Yes. So in the last class, we were discussing about linear SHM and angular SHM. And in today's class, we have to do two things. One is that we have to discuss how to calculate time period. What are the methods to calculate time period or the angular frequency of a simple harmonic oscillator system? Okay. Now you see there can be different systems which can oscillate into an SHM. Okay. Yes, I'll explain the last question as well. So there are many systems which can oscillate into an SHM. Okay, that is why simple harmonic motion or oscillations in general is extremely important in physics. Like for example, you can have some fluid dynamic systems which oscillate into an SHM. Then you can have some electrostatic systems which can oscillate in an SHM. Like if you let us say if you have two equal charges and you place another charge, any magnitude charge in between them, okay, then when you slightly displace the middle charge, then also the system oscillates in an SHM, provided your displacement is very small. Okay, so in fact, even in gravitation, you can have some systems which oscillate into an SHM. All right. So everywhere you'll see, and in fact, even your uh, molecules, you can assume that when you have very small displacement, they oscillate in an SHM. Although in molecular physics, you guys will study that it is not exactly simple harmonic motion. There is some unharmonicity, okay, which is expressed via physical constant, that is unharmonicity. Okay. So one student is saying that please revise the last question. So let us see. What was the question? This is the question. So I have just uploaded the first method to solve it, which is very lengthy method. So obviously that won't be very much suggestible in your examination. But there can be some case where you can only use that method only. Okay, like for example, you are given a random system. You have to find the force on a particular particle. Okay, and that force comes out to be proportional to negative of displacement. Okay, for a small oscillation. This you have to first do through the binomial expansion. And if it is coming proportional to minus of displacement, then you can find out what is the time period and so on. Okay. So anyways, this was the question which was asked in JAM 2011. Now, this type of question you will see in the assignment, and there are some miscellaneous problems also there in the assignment, which we have added. So that will also, you'll also find these kind of problems over there. So particle of mass small m is moving in a potential this, where omega naught and a are constants. The angular frequency of small oscillations for SHM about the point of stable minimum of V of x is. Okay. So in classical mechanics, in some places we say that this potential is same as potential energy. Now, not always this will happen. हमेशा नहीं होगा ऐसा. बट कुछ केसेस में हम ऐसा मान लेते हैं कि पोटेंशियल ही पोटेंशियल एनर्जी है. कहाँ नहीं होगा, बहुत जगह नहीं भी होता है, जैसे कि फॉर एग्जांपल ग्रेविटेशनल सिस्टम, सो पोटेंशियल एनर्जी इज डिफरेंट, पोटेंशियल इज डिफरेंट. एनीवेज, electrostatic system may be same, both are different. So this is the potential energy given to you. Okay. half m omega naught square x square plus a square by 2m x square. Okay. So clearly you can see that there is an extra term a square by 2m x square which is not constant. If it were a constant, मान लो वो constant होता second term, then we could have said that the system has a stable equilibrium about x equal to 0. Here, because there is a term involving x, a square by 2m x square वाला जो term है, due to that term, your stable equilibrium point is not at x equal to 0. Okay. So first, you have to find where that point is. ठीक है. Small oscillation के लिए where that point is my first task. Okay. So I have to try to express in this term. You have to try and express into this term. Okay. So stable equilibrium point is somewhere random. All right. So this is the method one. So what you do is you find stable equilibrium point first. Okay, let us see how we do it. So first, so our aim is to do f equals to some minus k times x. ठीक है, ये हमारा aim है. This is our aim for small oscillation. Now, because the system can have large oscillations also, so there will be some extra terms. ठीक है, इसमें कुछ extra terms होगा which can be neglected. You have to neglect the extra terms. Okay. So you have to express the force into this format. This is your task for method one. Okay. Now I'll tell you the easy method also, so don't worry. So this is the force, and force can be written as in terms of potential as minus du by dx. Okay, or minus du by dr in general. But because only x variable is involved in u, that is why we have done minus du by dx. Negative gradient of potential energy is force. Next step is, so I'll have a pointer. Next step is this one. So when you calculate the F force, this is the force. Okay. After taking the derivative and all. So you see this quantity m omega naught square, this is not k. ये k नहीं है. This is not k. This would have been k. ये k होता कब? जब second term नहीं होता. X dependent term नहीं होता. If because of this particular term, that thing which is multiplied with x is not k. Okay. Now you find stable equilibrium point. You have to find what x equal to x naught, which is the stable equilibrium point. For doing that, you equate force to zero. Force को zero से equate कर दो. Why? Because at stable equilibrium point, the force is zero, right? The force is zero. Like imagine a system oscillating in SHM. What is the force at the mean position? It is zero, right? Minus k into zero. Or it is force is minus k x minus x naught, where x equal to x naught, which is the mean position or the stable equilibrium point. So it makes the force zero, right? तो force zero हो गया है, उससे you find x. So this is my stable equilibrium point. This is the point where my force becomes zero. So that is why this is the stable equilibrium point x naught. All right. Now I have what I have to do. My task is to prove that for small oscillation, force is proportional to or force is equal to some minus k times x minus x naught and neglected terms and some neglected terms, other higher order terms. Okay. So when I do this, then I can, so I will do this through binomial expansion, and then I can extra time period या ओमेगा जो भी asked है वो निकल जाएगा, right? Then you can put it into omega to find the omega. Okay. So my task is to extract this minus k through binomial expansion. So now I know that small oscillations are about x naught point. x naught point के about होगा, तो x naught point के about बाइनोमियल एक्सपांशन लगा दीजिए. ठीक है. So this is what we have done next. Okay. F of x naught is 0. First step. And we know that f uh, is proportional to minus x naught. Right. So,
सर,
so this is, yes.
सॉरी इंटरप्ट किया आपको। सर बोल रहे थे कि जैसे आपने फर्स्ट डेरिवेटिव करके फोर्स को इक्वेट कर दिया जीरो के साथ, जिससे कि हम लोग स्टेबल इक्विलिब्रियम पॉइंट हमें मिल सके, जिससे कि
हाँ.
उसको एस के टर्म में ले आ पाओ। तो फिर हम लोग के उसको सेकेंड डेरिवेटिव करने के बाद भी तो लाइक हम लोग तो नतीजे में पहुंच सकते हैं कि जिससे कि सेकेंड टर्म नेग्लेक्ट हो जाएगा, बाइनोमियल एक्सपेंशन यूज ना करे तो।
नहीं 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 नहीं, तो आप ऐसा मान रहे हो ना कि x इक्वल टू 0 मीन पोजीशन है. ऐसा क्यों मान
हाँ
रहे
जी,
हैं? ऐसा आप क्यों मान
क्योंकि
रहे हैं?
वो
वो तो कहीं
स्टेबल
पे
स्टेबल पॉइंट है।
नहीं, वो स्टेबल पॉइंट नहीं है. सेकंड टर्म x, सेकंड टर्म में x है ना. देखिए.
हाँ, वो तो एक्स है आपका।
हाँ, तो दैट इज व्हाई दिस इज नॉट द स्टेबल इक्विलिब्रियम.
नो सर, वो नहीं, हमने वो हम नहीं बोले, वो पता है मुझे। मतलब
हम्म.
जैसे आप यहाँ पर बाइनोमियल एक्सपेंशन यूज कर रहे हैं इसको निकालने के लिए, हम लोग के सेकंड डेरिवेटिव यूज नहीं कर सकते लाइक d2u/dx2, ताकि
वही तो
जिससे कि हम लोग
सेकंड
को।
वही तो मेथड 2 है. वही तो इजी वाला मेथड है. ये
ओके,
इंट्यूटिव मेथड है. दिस इज द इंट्यूटिव अप्रोच कि कोई भी प्रॉब्लम आए तो उसमें क्या करना है आपको बेसिकली. ठीक है.
राइट
दिस इज
सर।
द
ओके,
इंट्यूटिव अप्रोच. ओके. दैट
थैंक
इज
यू।
द मेथड 2 जो आप बोल रहे हैं, विच इज द मेथड टू बी फॉलोड इन एन एग्जामिनेशन. ओके. So I'll just explain this one in short. So, so I said that f of x is proportional to, here in the right hand side, f of x is proportional to minus of x minus x naught, because oscillation is happening about x equal to x naught. That is why this expression, right? So I put x as what, x plus x naught. I replace x with x plus x naught. तो x को x plus x naught पुट करोगे तो it will be minus x. ऐसा क्यों किया? वाई डिड वी डू दैट? वाई डिड वी रिप्लेस x with x plus x naught? By doing this, I can express f of x plus x naught proportional to minus x. अब यहां पे जो प्रोपोर्शनैलिटी कांस्टेंट होगा, द प्रोपोर्शनैलिटी कांस्टेंट इन दिस पर्टिकुलर एक्सप्रेशन विल हेल्प यू फाइंड आउट द ओमेगा सिंपली बाय रूट ऑफ k बाय m, राइट? अब यहां पर जो प्रोपोर्शनैलिटी कांस्टेंट आएगा, वट एवर द प्रोपोर्शनैलिटी कांस्टेंट इज देयर इन दिस एक्सप्रेशन ऑफ फोर्स f of x plus x naught will give you the answer basically. Okay. So that is what I have written in this particular step, that you need to extract k from this particular thing. अब देखो, now what we have done is f of x we had already calculated through the derivative thing minus du by dx. ठीक है. उसमें I put x plus x naught. Okay. Now I know what x naught is. x naught भी निकल चुका है, which is the stable equilibrium point. Okay. So I see what are the terms. I see what terms are there. Okay. When I put x plus x naught, so first term have x plus x naught, second term has x plus x naught. Now what you have to do is you have two terms. एक में x plus x naught है, एक में 1 by x plus x naught to the power 3 है. So you do binomial expansion. Now I know it is a small oscillation. So x divided by x naught will be lesser, will be very, very less than 1, right? X divided by x naught will be very, very less than x common later. You have this term 1 plus by x naught to the power minus. This formula, we should retain the first and the second term only. This is the first term, this is the second term. So you terminate it to वन प्लस एन एक्स, ठीक है, उसके बाद द अदर हायर पावर टर्म्स विल बी जीरो, विल बी ऑलमोस्ट जीरो, ठीक है। तो व्हेन यू डू दिस यू गेट this thing, you get this thing. Okay, so this is your k, this particular value is k. All right, then you put it into omega and you get the answer. Okay, so this was the method, and you can simplify it to get omega is equal to 2 times omega naught. Omega naught was a constant given into the potential energy, right? Even if you don't understand this particular approach, there is a simpler method to do the calculation. Okay, so next we'll be discussing that only. So do you guys have any doubt in this particular method?
Sir, I have one doubt to ask sir, regarding this one. So, as you told that you have used this for the intuitive way of understanding that how do we actually get in rid of the
Yes.
second and also to get the actual answer. So, sir,
Hmm.
what could be the like, for example, sir, without solving in the point of, without solving in the perspective of getting the answer, most of
Hmm.
as this problem has two different terms, different x dependencies. So, sir, what is it actually physically signify means what like
Okay,
this
okay.
also this is also a simple harmonic oscillator. This also acts as a simple harmonic oscillator. But what do we physically signify from that? That we are having two different x dependencies.
Hmm. Good question. Very good question. So, what it could mean is that you have two kinds of forces into the system and they are getting linearly superimposed. There are two kinds of forces into the system and they are getting linearly imposed. This is what the meaning is. One force is x to the power 1, proportional to x to the power 1, and the other force is proportional to 1 by x square. Both are getting added with different proportionalities. So this is the meaning. You
Right,
can
sir.
imagine like molecules. So molecules have van der Waals forces, okay, which is then electrostatic. है ना, electrostatic force होता है van der Waals force. Like,
Yes, sir.
हाँ, so there is a negative charge, negative this electron cloud, and there is a positive charge. Of course, this is not the correct picture of the atom. This is the wrong picture of atom, but you can imagine at least
Right, sir.
through this model. So this type of force, right? So it has 1 by x square dependence, right?
Hmm.
So,
So, sir, the
hmm,
main thing is that, sorry for interruption, sir, I got your point. So, like
huh,
it's like in molecular spectroscopy or in molecular physics, uh, uh, whenever we used to study about that, we have something known as the Lennard-Jones potential and all those kind of
yes,
uh,
yes, yes. It
in
has to do with that only.
that
Yeah.
case, it will be power of 6 dependency and 12 dependency. So, in that kind of forces, sir,
Huh.
as Leonard Jones potential actually will not been actually been proven that why do we really get that kind of 6 or 12 power dependencies. So, the similar to this one, so as you told that this could be a superposition of two different forces. So, this is actually the practical cases which we are dealing with, right? But means the force which is being given in the question is or
No, no,
any
no.
type
This
of
is
force.
not a practical case. This is not a practical case.
Okay.
Hmm.
Means in real life situations, this kind of forces might arise due to the different potential dips.
Yes, yes, definitely. They can arrive.
Okay, okay, sir. Okay. Thank you,
You'll
sir.
have.
Sorry for interrupting.
Okay.
Yes, sir. Thank you, sir.
So then we have the method two. Let us copy the same question. Method 2. So this should be your go-to method to solve such questions where the potential energy given or the force is given. Okay. So what we are doing actually is force or potential energy is given and time period needs to be calculated, or omega, of course. All right. So this is our problem statement. You can have different problems in such things. Okay. So now you have to understand that we were doing force equals to minus kx, right? This is for purely an SHM, not a system which can behave like an SHM. Okay, so I'm not talking about that. This is purely an SHM. Okay. So what you can say is that you take first derivative, or let us say this is about x naught. Let us say this is our mean position. X equal to x naught is mean position. All right. So this is a SHM. And this is f as a function of x. Now if I take derivative, then what am I going to get? This will be minus k into minus x naught. Okay. Uh, what is the mistake that I am making? Is there any mistake? वन, अच्छा वन वन हो जाएगा, right? This will be वन, वन minus zero. Sorry. So this is the thing. So this is minus k. Now you take it at x equal to x naught, the mean position. Okay. So it will still be minus k only, right? It will still be minus k only. So you have this one thing. If I take the modulus of this one, first derivative of x naught, first derivative of force at x equal to x naught, and I take the modulus of it. So this will give me k. ठीक है, तो k ऐसे मिलता है. This is how you get k. All right. So then you can directly write what the angular frequency of the system is. Okay. Be it small oscillation or be it any kind of system. All right. So this is the thing. So f, so sorry, omega is under root f dash x at x equal to x naught and the modulus of it. So you have to make it positive, right? To make it positive, divided by m. So just use this method. That's it. Now I know that force is minus du by dx. So if I am saying that force at x equal to, sorry, so f dash will be minus d square u by dx square. Okay, because f dash is df by dx, of course. Now I'm doing it for one dimensional motion, obviously. So that implies uh, f dash at x equals x naught is equal to d square u by dx square at x equal to x naught. So because this thing is k, so you can say that this thing is also k. So this is how you calculate k. Calculation of k. Now, of course, this can be done through general method. This can be done through a general method by Taylor expansion of force about the mean position x equal to x naught. So I'm not going into the Taylor expansion. You can see into the text for a general case because this was a purely SHM case, right? And what I am saying is this can be applied to a system which behaves like an SHM in small oscillations also. Okay. So I am generalizing the thing but using a special case. So you should understand what cheating the teacher has done actually. Okay. So to avoid the Taylor expansion, I have done this. Okay, so this is how you calculate this K, which is the double derivative of U or the single derivative of force at the mean position. Okay, this is K. And you just put it into omega. Or you can calculate time period using this formula. Okay. So now this problem is very simple. U is given to you, just take the double derivative and also find the mean position first. Then put the mean position into the double derivative thing and you'll get the answer. Okay. Now everyone try that question through this particular method.
Sir,
Yes.
hello.
Yes.
Yes, sir. Sir, since the in the previous example, which in the previous method which we have used in that case, we have put that f equals to 0. So in this case also we have to put f is
Yes,
equals to
yes,
0,
yes.
right?
Definitely, definitely. That is the only method to find stable equilibrium point.
Okay,
Yeah. Because at stable equilibrium point, force is zero. So you are
right.
doing back calculation of x equal to x naught.
Okay. So on performing the first derivative, I got something as a square by 4 omega naught square whole to the power 1 by 4, which is the value of x I got.
First derivative.
Yes, sir.
No, first derivative you will get x cube in the denominator.
Now that I got. I
Mm-hmm.
got m omega naught square x is equals to a square by 4 m x cube. That I
Okay.
got. But
Okay.
after rearranging that
Ah.
x, I got x to the power 4 is equals to a square by 4 omega naught square.
Hmm.
So that is x, but I have to find the potential, right? So in that case, that this same expression I will differentiate twice, a second time, with
No,
respect to
no,
x.
now it is not required because I think you have calculated force first, है ना? You have
Yes, I
calculated
got
force.
4.
So you have to derive it again. Yeah, correct.
Yeah, yeah,
You have to
right,
derive
sir.
it
Okay,
again. Yeah.
okay, sir. But this is not U. This is not the potential energy, right? This is the actual displacement which I got x.
This is the stable equilibrium point x naught that you have calculated,
Okay.
and that when you take first derivative of u, you get f. Then you take another derivative, you get f dash.
Oh, right, right. Okay.
So I'll solve it over here, and you guys can just look at the solution, and also you can try on your own. So first we are calculating the force, right? This is how we calculate the force. A square by 2 mx cube was given, right? X square was given. So this becomes minus of m omega naught square x and minus 2a square by 2m x cube. So 2 gets cancelled. This is the force. And using this force, you calculate what is the stable equilibrium point. So you put x equal to x naught and say that it is 0 because it is the stable equilibrium point or the mean position. So minus m omega naught square x naught minus a by mx naught cube equals to 0. So when you do the rearrangement, you're going to get this thing. So x naught to the power 4 is a square by m omega naught square. So you'll have to the power 1 by 4. Of course, there will be many roots. There are 4 roots, right? But we'll have to consider the positive one.
So I think you made a mistake. Sorry for interruption, sir. I think so because on performing the first derivative,
Mhm.
we in actually in expression we have that half m omega naught square x square plus a square by 2m x square. That we have.
M square. M square is there, right? M square.
Right,
This
right, sir.
was a mistake. Yeah. Now this is a stable equilibrium point or the mean position. Then I have to take the double derivative using the force expression. Let this be equation number 1. So by 1, I take the another derivative, which I'm going to get as negative of m omega naught square, and this will be 3 divided by x to the power 4. Okay, so this will be m omega naught square plus 3 divided by x to the power 4. So 3a by m x to the power 4. And what I do is I put x equal to x naught over here. So x equal to x naught, and x naught I know. So when I do that, I am going to get, and also let us take the modulus, so it will become positive. It will become m omega naught square plus 3a by m, and this thing a square by m square omega naught square. Uh, so this becomes to the power 4. So a square m square omega naught square. So 1 m gets cancelled. 4m omega naught square, right? So this is nothing but k. So omega can be written as k by m. So this becomes 2 omega naught.
So can you give us one more such kind of a problem? Or after this class you will gonna send us?
Yes.
So like after this class you will going to give us some more problems like this one, or in this class only you will gonna give us this kind of problem?
I'll send some problems if you want for reference, or I
Yes, sir.
can mark the number in the assignment also. Okay, so I'll send
Yes, sure,
a
please,
few
so that
problems.
we can practice. Yes.
Yes. Or let me check into the assignment, then we can solve it. Okay, so let us proceed with our discussion. So in the last class, we had discussed linear SHM and angular SHM. So in linear SHM, we saw that acceleration was minus omega square x, right? Of course, mean position is at x equal to 0 only, for example. So omega came out to be root of k by m. Similarly, in angular SHM, torque will be uh,
Omega
some
square
minus,
theta.
some minus k dash into theta. Okay, so here there was force expression minus k into x. All right. So this I have just made it different from the k. That is why I have written k dash. So this will be I into alpha, right? Where alpha is the angular acceleration and I is the moment of inertia of the object. Okay. So this is minus k dash into theta. So now alpha becomes minus k dash by I into theta. So just like we wrote omega as k by m, here in angular SHM, we can write omega as root of k dash by I. K dash is again the proportionality constant in the torque proportional to minus of angular displacement thing. You know, angular displacement is theta. So you can do like this. Now, if I have to generalize the thing, so here what we did was, in the linear SHM case, what we did was we generalized omega. We generalized the omega, right? Where omega was f dash x naught, right? Modulus divided by small m. So this is how we generalized it. Or we can also say that d square u by dx square x equal to x naught by m. So similarly, if you want to generalize this omega in the angular SHM case, then you need to make it first derivative of torque with respect to theta. Okay, first derivative of torque with respect to theta at theta naught, which is the mean position. Because let us say theta is equal to theta naught is the mean position. It might be 0 in some cases or not 0 also. We take modulus of it and divide by moment of inertia and not the mass. Okay. So everything you can try it for a simple pendulum. Okay. Whose moment of inertia will be m into L square, right? M into L square उसका moment of inertia हो जाएगा. So that way you can try. And this can be then written as, of course, uh, double derivative of u with respect to theta at theta is equal to theta naught and divided by I. Okay. For a simple pendulum, let us say, because this is massless, the string is massless. So the moment of inertia of such system will be ml square if this is the length L. Okay.
Then the situation will be changed for a physical pendulum, such as a compound pendulum.
Yes, the situation will change, of course. So there will be compound pendulum, there will be two equations. Okay. Two equations instead of one. Okay.
Okay.
Now let us discuss different types of simple harmonic oscillator systems. Okay. So we have already discussed a spring mass system, which was something like this. And when you displace it through a magnitude x and leave the system, then it oscillates in a SHM. Okay. Where omega was root of k by m, where k is here k is spring constant, right? This is the spring constant. So this is the angular velocity, sorry, angular frequency of the motion, okay, of the SHM. Why it happens? It happens because restoring force is minus kx, right? Where this is a spring constant. So this way you calculate the t also, which is 2 pi under root m by k. This is the time period of um, simple harmonic motion in the spring mass system. Okay. Now, this was case 1 for a massless spring. Remember, this formula will be valid only for a massless spring. Okay. For a massive spring means that the spring also has mass, the formula will be different. Okay. Another case can be spring mass system against gravity. Okay. So spring mass system against gravity. So you see this spring when in equilibrium, this is already stretched. This is already stretched because this is an equilibrium, let us say. So there will be downward force, there will be an upward force. Okay. जो भी stretch हुआ है, let us say y stretch has happened due to the mass against the gravity, right? Against the gravity, let us say y stretch has happened, so the upward force will be ky, which will be restoring force, right? So the equations balance in such a way that the equation of motion is still the same, which is minus ky. Okay.
mg equals to minus ky.
Img equal to minus ky. So this is the equilibrium condition which you are saying. Okay. There was a question in JAM 2026 based on the equilibrium condition. But what I am saying is that force still comes out to be minus ky. This we had proved in the class. Okay. So because the force is still the same, um, just the variable has changed to y, and that is the displacement. So because the force, the expression of the force is same, that implies that the time period will also be same. Okay. Time period is same. Now, you guys have to tell me one question, one answer. Let us say this is theta, inclined plane, and I have a spring mass system over here. Okay. And again, the block is in equilibrium, and you give a slight displacement in this direction below the down the incline by x, let us say. Okay, here if you give slight displacement along y direction, only then the oscillations will start. Similarly, here you give a slight displacement after the equilibrium position, then you have to tell me what will be the time period. Will it be different? Will it be the same? You can try and make the free body diagram of mass m. Now there can be a question in the examination asking you guys that how these three systems are different or how these three systems are same.
So is the inclined plane friction or frictionless?
Frictionless. Let us consider
Frictionless.
everything frictionless.
So, sir, in that case, sir, as much I know, the time period will remain same since we don't have any dissipative forces along with the motion.
That is correct. But it would have been better if you try the equation of motion. Try writing the equation of motion.
And I'm doing it. I'm doing it. Yes.
Okay. So you guys can comment also in the chat if you want. The question is, will the time period be same of this particular spring mass system or will it be different? Okay, so the answer is time period is same. Because also this is also against the gravity only. Okay. Now the question is, what is different in the three cases? Is there something which is different? Because the time period is certainly the same. Is there something which is different? Anyone? As far as the SHM motion is concerned. Now, I
So they
don't
are
want to. Yes.
components of the angle. The resolution of the components of the angle will be there. One will be the mg sine theta in the opposite direction of minus ky. Another will be the
That is
mg cos
okay.
theta.
That is okay. I'm not asking that. I'm asking that how the dynamics differ. Basically, how the dynamics of the problem differ if all the three are SHMs with the same time period. Is there something else which is different? Now, if I consider this as the y-axis, and I consider this as the y-axis, are the motions along the y-axis different or the same? They seem to be the same, right? Because choice of coordinate system is with us only, right? We can choose whatever system we want to. So there is a statement often used in physics that nature the laws of nature are silent over the choice of coordinate system. Okay, so if you change your coordinate system, your law should not change, the law should remain same, right? Anyways, so there is something which is different. ठीक है, यहाँ पर देखिए क्या है. Let us say L naught is the natural length of the spring. If I start measuring from here, let us say x equal to 0 is here. So the mean position will be at x equal to x equal to L naught. This is the mean position. You can put it x naught also, x naught equal to L naught, you can say. This is the mean position. But this is not the mean position for the other two cases. यही different है. Rest everything is same. The dynamics will be same. Okay. Can you guess what will be the mean position over here? Like if you take this position as y equal to 0, so the mean position is at y equals to uh, L naught plus, using the equilibrium condition, you can find out the equilibrium expansion or equilibrium, what you can say, equilibrium stretch. ठीक है, which will be mg by k. ठीक है, तो यहां पर मीन पोजीशन ये है. In the case 2, this is the mean position. And in the case 3, of course, there will be an angle. So you can check whether it is sine or cosine. Okay, simply. So there will be angle dependence in the second term. mg by k में एक angle dependence आ जाएगा, sine या cosine जो भी होगा. ठीक है, तो sine 0 is 0. So yeah, so there will be sine term. Okay, so L naught plus mg by k sine of theta.
So
This is
there would be a different time period will be like 2 pi root under m by g sin theta.
no.
Will be,
Time period will be same. 1,
no, that
2, 3. Only the mean position is different. The mean position is different. Time period is same. Okay. So let us take a small break and then we'll discuss some other systems of simple harmonic oscillator. So we will meet at 7:10.
right. So why are they same link?
Yes, any doubt? Siddharth,
So why are they same link? We will join.
why am I?
Means the there would be a break for 7 10 minutes, 7 minutes of break. So okay, do we have to quit or we have to stay in the class?
You can stay in the class. No issues. You can stay.
Okay.
Okay. Okay, so let us resume. Now let us think about two types of cases which bring practicality to our system. Okay, so first assumption that we did was that spring was massless, right? Which is actually not. Second, um, is that one student was already saying, Siddharth was saying that do we have to consider friction? So if we consider friction, then what? Okay, friction. We have assumed that friction is zero, which is not. So in such cases, like how you can then proceed. Okay. So when you have this kind of non-ideality in the system, then you can use the energy method to get the time period. Okay. So um, the finally the thing that we calculated was time period, right? So अगर इस type का case है, if you have these kind of cases and you have to find time period, then you can use some method 3. You can use some method 3, which is energy method to find capital T, right? So this is the method 3, using energy, total energy, to find time period. Okay, so let us deal with these kind of cases. Now, of course, these all the things that I'm discussing in the initial classes are very much related to purely classical mechanics, Newtonian mechanics, basically. Okay, so I want you guys to study these topics or have a reading of the solved examples at least from H.C. Verma book. Okay, so I'll just share one thing with you guys. So this is the H.C. Verma book that I have, and I have the signature of H.C. Verma sir. I don't know if it is visible. Not visible actually. Okay. So what happened was when I was research scholar in the IIT BHU, so H.C. Verma sir had visited our institute to give a talk and communicate with the professors and research scholars of physics department. Okay. So he also visited our lab and he was interested in what research we guys do. And so then we all proceeded to the talk. He gave a 1 hour talk in the physics department, and everyone, and mostly the MSc students, were more interested in taking selfie with HC Verma sir. Okay. And there was only one, so the research scholar were more decent that they did not try to disturb HC Verma sir. And so मतलब रात हो रही थी उस टाइम पे, तो सब लोग फोटो ले रहे थे सर के साथ में, तो फ्लैश ऑन हो रहा था, तो इतना ज्यादा लोगों ने सराउंड कर लिया था सर को कि ही वॉज नॉट एबल टू सी ऑल्सो. ठीक है. Then what happened is that I was not interested in taking a selfie, but I urged sir to give a signature on his book. So I had his book with me. I was the only scholar which took the signature and not the selfie. Okay. Anyway, so the point is that you see the solved examples of SHM. Okay. तो सिंपल हार्मोनिक मोशन का सॉल्व एग्जांपल्स जो है HCV से वॉल्यूम 1 से देख लो आप. तो इट विल गिव यू गुड आइडिया. ओके. because otherwise, if we discuss each and every concept, it will take a very long time. Okay. Now let us consider that the spring is heavy, block attached to a heavy spring. Now the block has mass. Also, the spring has mass. Let us say it has a mass ms. Okay. So what will happen is, of course, the net oscillation will change now. The dynamics of the oscillation will change in such a way that the time period will change. Okay. This will change. So let us see how to approach this particular problem. Suppose this system is set into oscillation by displacing it through some amount. Okay. By displacing it into some amount and you have released. So it will undergo oscillations, right? Let us say the speed of this block is x dot, okay, dx by dt, because this displacement, some instantaneous displacement is small x, okay. And let us denote the y variable for the spring. Okay, now what will happen is the spring that is at the part of the spring which is attached to the block will have the velocity x dot only, right? Because x dot is the velocity of block. Okay, this is the velocity of block, which is dx by dt basically. Now the parts which are very near to the block will also oscillate with the speed x dot. But what about the parts which are near to the rigid support? So this part will have zero velocity, right? And this part will have x dot velocity. So what about a part somewhere in the middle? Okay, so let us say it has y displacement from the origin O, and then let us say that this part has a velocity y dot. Okay, and if you have linear increase of the velocity from x equal to 0 to x equal to a, let us say, or whatever, x equal to x plus a, whatever you want to take, l plus a in fact, no sorry, l plus x. Okay, this is l plus x, right? Or you take the amplitude x plus a, l plus a, sorry. So whatever. So let us say the velocity of spring is y dot. Okay. So if you have linear system, then you can say that this y dot is proportional to y only. Y dot is proportional to y only. And the limits of the problem are that for x equal to 0, y dot should be 0. And for x equal to L, y dot must be uh, x dot. Okay. So of course, multiplication by y by L will make sense for y dot. Okay. So y dot becomes y by L into x dot, right? Now when y is equal to L, अच्छा ये x नहीं y होगा because we have assigned the variable y, right? Displacement वाला जो variable है that is y. So you take it y in fact. Y equal to 0. So finally, this is the expression. If you have any doubt, please ask. This is the expression of velocity of spring in terms of velocity of block. Y is displacement from the rigid support. Now
So
kinetic
that
energy.
y, sorry
Yes.
for interrupting, sir. So that
Yes.
y you have chosen as the coordinate to represent the extension of the spring, right?
Position of the small element on the string. Okay. Let us say this
No,
particular part.
no,
Uh-huh.
no, sir. Like y you have chosen as the coordinate with
I'll
which you
explain.
are working.
I'll explain.
Okay,
So I am
okay.
taking a small part of the spring. I'm taking a small part of the spring because every part has different velocity. This you agree?
Yes, sir, I agree.
Huh. Because the leftmost part has zero velocity, rightmost has x equal x dot. Okay. Now this is a part which can be called as element, has dm mass and let us say dl length. Okay. Dm mass, dl length. Okay. Now it has a position y. Let us say it has a position y. If this is y equal to 0, then it has a position y is equal to y. Okay. And if this y is
Right.
equal to L, then it has to have the velocity x dot. So that is what is being satisfied through this particular expression.
If y is equals to L, then it will satisfy the value of x dot. Okay, okay. So by
Uh-huh.
the limit. Okay,
Yes.
got it.
Now, of course, there could be some other expression also, but we are considering a linear case that the velocity linearly increased when we move from y is equal to 0 to y is equal to L. Okay. Now, I am finding one physical quantity that is kinetic energy of the spring. Okay. Now, you might think why we are interested in the kinetic energy because this is energy method that is going on. Okay. So, this is yet another way to calculate the time period when you don't have a very ideal system. Okay. So, we are trying to calculate kinetic energy of the spring, not the block. So, the kinetic energy of block, of course, will be half m x dot square, right? Now I have to calculate the kinetic energy of spring. So I'll have to integrate the kinetic energy of the small element dm, right, of the spring because every part has different velocity, right? So what I can do in such cases is I can integrate half dm into y
Y
dot.
dot square.
Yeah. So this is what I can do. Velocity of element square. Yeah, correct. So y dot is y by L into x dot half dm y square. So y x dot by L square by this expression. Yes, okay, correct. Now if we have a uniform spring, we have uniform turns per unit length in spring. Only if we have uniform turns per unit length in the spring, then we can write an expression that is the uh, total length. What you can say is, not the turns per unit length. I'm sorry. We don't require the turns per unit length over here. If we have a uniform mass spring, I'm trying to calculate dm over here, which is the mass of element of the spring. If we have a uniform mass, then of course I can say that small element mass divided by the length of the small element, that is dl, will be equal to total mass by total length of the spring. Total mass of the spring is ms and total length of the spring, let us say, is L. Okay. This is total mass and this is the total length. So this you use many places in the physics. So total thing divided by total thing is the elemental thing divided by the elemental thing. Okay. So this you can use only when you have uniformity. Okay. So then dm can be calculated like this: ms divided by L into dl. You put it over here and you get the kinetic energy. So the kinetic energy of spring will be half outside integration ms divided by L dl. dl can be called as dy because the variable involved over there is y. So it is a small change in y, right? dl is actually dy only, because dl, small change in length, is small change in y. So half this thing, and y square by L square, and x dot square. Okay. Now there should be something such that the such that the x dot gets cancelled. Okay. Do you get something like this? If I put y dot in terms of y, then x dot will get cancelled, right? Y dot. But then I'll have y dot. I don't want y dot in the expression. I want x dot. So what can I do? Can you suggest a method to solve it further? dy. Acha, variable is y only. Correct. The variable is y. No issues. So this is y equals to 0 to y is equal to L. I hope you agree.
So
So
that x dot square can be taken as the constant as it is actually
correct,
the velocity of the
correct,
mass.
correct.
Yes.
Yes. So
Because
so
the
I was
integration limit, the dummy integration is only on the variable y, not on L
correct.
or x dot square.
Correct. So this can be treated as a constant. So half ms x dot square can be taken outside, and there's a 1 by L cube which can come out of this particular expression, and this will be y cube by 3. So L cube by 3 after putting the limits. Okay, this is after putting the limits and all. This is what you get. So L cube gets cancelled, and this is the kinetic energy of the spring. The kinetic energy of spring comes out to be half ms by 3 x dot square. Now this is the total kinetic energy of the spring. So which tells you a very important thing, because kinetic energy, because the velocity of each element of the spring is different, right? And if you consider the whole spring as a whole, the mass of the spring is contributed as 1/3. Okay, so you can call this as effective mass of the spring. Why am I calling it effective? Is that as compared to the kinetic energy of the block, it is getting contribution 1/3 as compared to its टोटल मास. ठीक है, टोटल मास का 1/3 ही कंट्रीब्यूट हो रहा है काइनेटिक एनर्जी में, ड्यू टू द फैक्ट दैट सम पार्ट ऑफ द स्प्रिंग इज डेड, है ना, एंड ऑल द पार्ट्स ऑफ ब्लॉक आर मूविंग ओनली. So now I can write the total energy of the system. Total energy of the system. This will be kinetic energy of the system, that is half m x dot square,
Plus half kx squared, the potential energy.
right, plus half ms by 3 x dot square. So this is kinetic energy of block. This kinetic energy of spring. and there is a single potential energy into the system, that is the potential energy of the configuration of the system. So this is half kx square only. It won't change with the mass of the spring, of course. Okay. So dE, what you do now is equals 0. Okay. Since energy is conserved, or you call it constant, due to absence of dissipative forces. Now, we are assuming again over here that there is no dissipative force, there is no friction, there is no air resistance, there is no nothing. Okay. So absence of dissipative force. So you can say that time change of the total energy is 0. So as soon as you do this thing, so d dt of the energy, so this becomes mx dot into x double dot, because there will be derivative of x dot, right? Plus you will get ms by 6, um, sorry, ms by 3 x dot into d dt of x dot plus k x into dx by dt. दिस इज, अच्छा ये डेरिवेटिव ले लिया पहले ही, ठीक है. सो दिस इज dE by dt, right? This is the dE by dt, which is equal to 0. From the previous step, it is equal to 0. So, which means that m into x dot into x double dot plus ms by 3 into x dot into x double dot plus k x dot equals 0. Right? So I hope we have proceeded correctly. Now x dot gets cancelled from all three terms. So now x double dot into m plus ms by 3 is equals minus kx, right? So x double dot, which is the acceleration of the block, is minus k by m plus ms by 3 into x. So can you tell me what have we got? I'm not asking the time
SH,
period.
SHM, equation of SHM.
Yes. So what happens is when you equate the time derivative of energy with 0, for a conservative system, this will obey, right? dE by dt will be 0. So if you find out this dE by dt equal to 0 by putting the energy expression into that one, then you automatically get the equation of motion. Okay, so this is a way in general to calculate the equation of motion, or to arrive at the equation of motion. So this is nothing but equation of motion of block, not the spring, of the block. Okay. So automatically you see that there is a contribution of mass of the spring into the equation of motion of block. Okay. So obviously now it's very easy to extract what the what the time period of the system is. Okay. So of course the time period of the system now will become 2 pi
Sir,
under
I
root.
have one question to ask. May I?
Sure, sure.
Yes, sir. So my question is that dE dt, the derivative of the energy with respect to time, is equated to 0. Is only applicable for the cases as you have mentioned that we are having a conservative forces in which there no dissipation of energy or something like that.
Yes,
Or is it in
definitely.
general?
No, no. When you have dissipative forces into the system, then your energy becomes decreasing, right? So it can be this kind of graph versus time.
No, sir, I'm not
What?
asking that, sir. Actually asking you that derivative of energy with respect to time is equals to zero is only applicable for the energy conservation, like energy conservation in which there no dissipation of forces, dissipative energy is required, or it
Yes,
is
correct.
applicable for all the cases, only for the non-dissipated case, right?
Yes, only applicable for conservative system,
For conservative systems.
which
And the
means that
homogeneous.
only conservative forces are there in the system. Okay.
And say if we have any dissipative forces, then it will not be equals to zero. We
Yes,
get
it will
it.
not be equal to zero. It
Okay.
will not be equal to zero.
Okay.
So from this discussion, what we have studied is we have studied the method three. Okay. We have studied the method three to calculate the time period, right? So you have to keep in mind that you have yet another way to calculate the time period. All right. So this is method three. And now we can do one question related to the friction in the spring mass system. Okay. Are all the students following whatever I'm saying? Is the speed slow or is it fast or is it okay?
No, sir,
Please
it's good.
comment.
It's okay. It's okay.
Okay. What about others? Uh, Pradeep, Srishti, Pradeep, and Aryan. Are you guys following?
Yes, sir. So,
Okay. Good, good, good. Now I had to discuss a friction case. Okay. Let me discuss a problem related to friction. Now you guys can attempt the uh, assignment also. Okay.
sir, how I will get the assignment?
असाइनमेंट जो है आपके सेक्शन में अपलोड होगा, ठीक है? अगर नहीं होगा तो आई गेट इट अपलोडेड, ठीक है?
Okay, sir.
यू ट्राई द फर्स्ट असाइनमेंट ऑफ द waves and oscillations. Okay. Question is a horizontal spring mass oscillator has mass has a mass oscillating on the table with friction coefficient as 0.1. So it is both, let us say, kinetic and static friction both. Now, natural frequency of the oscillator is 10 Hertz. Natural frequency of the oscillator means without any dissipative force. Okay. The system is given an initial amplitude of 0.2 meter. The total distance traveled by mass before it comes to a stop. G you have to assume as 9.8 meter per second square. 160 meters, B 80 meters, C 40 meters, D 20 meters. Now, because this is an illustrative example, I'll solve it. Okay. am not waiting. So in this question, a horizontal spring mass oscillator has a mass oscillating on the table. This should be on the table with a friction coefficient of 0.1. Now, natural frequency of the oscillator is given to be 10 Hertz. This is not the angular frequency, this is just the frequency, which is 1 by time period, of course. The system is given an initial amplitude of 0.2. The total distance traveled by mass before it comes to a stop is close to. Now you see there is dissipative forces in the system. So system will come to a stop, which means that total energy will get on decreasing to a point where kinetic energy will go decreasing and it will come to a stop, so it will become zero. Okay, of course the potential energy will also decrease to zero because there is no displacement at the later stage. So what you can do over here is, if you have studied a little bit of work, energy and power chapter, so there you will see that the work done by dissipative forces, the work done by non-conservative forces or the dissipative forces brings about a change in energy. So this is the way you can remember the expression, that is work done by non-conservative forces. This brings about a change in energy, right? So this will be EF minus EI. This is a nice way to remember this particular expression. And then there is another expression, work done by conservative forces. This doesn't bring a change in total energy, but it can bring a change in the kinetic energy. So this is kinetic energy final minus kinetic energy initial.
That's the work energy theorem, na, sir?
Yes, this is work energy theorem. So what is the work done by frictional force? Work done by frictional force is minus F. F is the frictional force and D is the displacement. Okay. Final energy is zero because it comes to a stop. It is given that it comes to a stop, and minus the initial energy. Initial energy is the total energy, right, of the mass oscillator, right? So it is half m omega square a square or half k square, right? The total energy of the simple harmonic oscillator without dissipation is half k square, right? Where k is m omega square. So this is what you can write. So now friction acts opposite to the displacement. That is why there is a negative sign. Okay. Wherever the displacement of block is, opposite will be the friction. And this d is the displacement after which the block comes to rest. Okay. Or the total distance. Distance after which block comes to rest. So this d becomes half m omega square a square divided by f. F can be written as mu into n, normal reaction. So mu mg, right? This is frictional force. Mm gets cancelled and then you can estimate the value. So mu is given as 0.1. Mass, I think, was not given. Amplitude is given to be 0.2 meters. Okay. So, so this is also given 10 hertz. So this is 2 pi by 10 hertz, like 2 pi into 10 hertz square. and there's a 2 in the denominator and 0.2 square. So this is 0.04 and divided by mu. Mu is 0.1. 0.1 into 9.8. So let it become 1. Approximately it is 1. All right, so this will become. So now you can do the simplification. 0.02. This is D. Okay. You can try calculating the exact value. Now pi square is nearly equal to 10 only, or in fact 9.8. So 9.8 gets cancelled. Uh, so this is 10 square. So pi square is 10 and 100. So 100 gets multiplied and becomes 2. So 2 into 4. So 8 meters के करीब शायद आएगा आंसर. ठीक है, you can check. Approximately it is 8 meters. Okay. Any doubt?
Sir, one more doubt, like this kind of question may appear in the examination in which there is a frictional force along with a drag force due to viscous medium. If there is a viscous medium,
हाँ, you can be asked such question also.
like for example, the velocity dependent on the v or
Yes,
v
yes,
square or
yes.
something like that. So in that case, sir, then work done of the non-conservative forces will be the addition of those two, right? The frictional force and the drag force, if there,
Yes, yes,
multiplied by the distance, multiplied by d.
yes, yes, yes. There can be
Right.
different, many type of questions. So you see,
Okay.
you can have about 100 to 200 variety of questions, okay? Because it can be related to any concept, but then the final outcome is that SHM is taking place. SHM is there, okay? You can have momentum conservation. You can have angular momentum conservation type of problems. You can have gravitation related problems. You can have electrostatic related problems. You cannot have magnetostatic related problems because magnetostatic system doesn't support SHM. You can have multiple systems. You can have a fluid dynamic system. Okay. So we'll discuss some of the cases, of course. Now, in the spring mass system, spring mass system, you can have combination of springs. Now, it is by common sense that if you have a system like this, connected by two springs, okay, spring 1 has a spring constant K1, spring 2 has a spring constant K2. So of course, when we try to oscillate such system, now not just against gravity, against any kind of thing, like you can keep it on a table also. Now, we are not interested in how the spring mass system is kept because the dynamics remains the same. We are interested on in what will be the effect of two springs. ठीक है, combination of spring का क्या effect होगा. So in such case, when you try to oscillate such system, when you move it through a displacement, let us say y, then there will be two forces into the system, two restoring forces, and that restoring force add up into the mass, right? Mass में add up हो जाएगा restoring force. So this type of combination of spring means that you have to add K1 and K2, है ना, इसका ये मीनिंग हो जाएगा basically, because the restoring forces add up when you make the equation of motion of the system. Another case, so here the K effective will be K1 plus K2. Effective um, means that this thing will be used to calculate the time period. So time period will be 2 pi root m by k effective, which is k1 plus k2. You can put k1 plus k2. Another type of system can be this, behaving exactly similar.
Series string combination.
Yes.
In a series string combination in which there would be k
Ah,
effective by 1 by k1 plus 1 by k2, because the total elongation will be x1 plus x2, right?
no, no. So I have written or. So what are the other system which behave similarly? Okay. So it can be this kind of system. It can be this kind of system where you have a mass m kept between two springs of k1 and k2, spring constants. Okay. Now k1 can be equal to k2. You can be given a problem where k1 is equal to k2 and so on. So here also what will happen is when you displace the system, now remember the system needs to be displaced along the y. ठीक है, y में डिस्प्लेस करेंगे तभी ये वाला फॉर्मूला आएगा. ओनली देन दिस विल बी द फॉर्मूला. इफ यू डिस्प्लेस अलोंग x, एक मैं होमवर्क दे देता हूँ. इफ यू ऑसिलेट दिस सिस्टम small displacement along x. Okay, so is it an SHM? This is your homework. Okay, you have to see if you displace this into in the x direction, so there will be some angular forces, like not angular, like the forces will make some angle, right? If you displace this block over here in x, so this is how the forces act, right? इस लाइन के along forces act करेगा तो वो SHM बनता है या नहीं बनता है? Does it become an SHM or it doesn't become an SHM? That you have to find. But we are talking about Y oscillations. Okay. Here also we were interested in the Y oscillations. So coming back to the problem, this system also behaves like this, right? So I'll just write k1 plus k2. It will make more sense. So there is a series combination of the springs when you have these kind of arrangements. Now, why does the second system behave like this? Because you imagine displacing the block by y displacement. So the upward spring try to attract it, okay, when you bring the system downward, and the lower spring tries to resist it. ठीक है? तो जब इसको आप नीचे लाओगे ब्लॉक को, when you displace it downward, then there are again two forces acting in the upward direction or in the opposite direction. Okay, and vice versa. Like if you give a positive displacement, then both the forces will be downward. So this basically, इससे क्या हो जाता है? Force becomes equal to minus kx, no sorry, minus k1 into y minus k2 into y. So k1 plus k2 basically, right? So that is why the same expression comes. So this is case 1, case 2, case 3. Case 3 can be two springs attached to a mass. Okay. Two springs attached in a series. K1, K2, and you have mass attached. Okay. Now this K effective of such system
Will be 1 by k1 plus 1 by k2.
correct.
Because the displacement is total, that x1 plus x2 will be total displacement.
Correct.
Right.
So you can prove it through the equation of motion also. So K effective will be K1, K2 divided by K1 plus K2. But you can have three springs also. So you can then remember this formula as a series, like uh, mathematical series, not this one. Okay. So you can have another term 1 by K3, 1 by K4, and so on. So this is the equivalent k. So similarly, the time period will change 2 pi under root m by k, which is k1, k2 divided by k1 plus k2.
Sir,
Yes.
can this kind of a question may arise in which both three combinations or both the two combinations are combined together, like in a series and a parallel combinations together?
Yes, you can have such combinations as well. ऐसे हो सकता है ना, जैसे कि
तो सर उन प्रॉब्लम के साथ कैसे हम लोग डील कर सकते हैं, ऐसे लाइक दोनों लाइक एक बार बोल देंगे?
हाँ, जैसे ये दिया जा सकता है आपको सिस्टम k3। ओके, अब ये दोनों सीरीज में है, like they look like both are in parallel, but the formula is of series, right? So k1 and 2 becomes k1 plus k2, and so this can be written as k1 comma 2, and equivalent of 1 and 2, and this thing k3,
सर
k3।
हाउ, कैसे सर K1 K2 आपका सीरीज में हुआ सर, समझ में नहीं आया, क्योंकि लाइक पहले वाला जो केस आप जो करवाए थे उसमें K1 और K2 तो पैरेलल में था ना, तो इसमें भी पैरेलल कॉम्बिनेशन का ही लाइक एक लॉजिक लग रहा है, तो कैसे सीरीज में ऐसे समझ में नहीं दिखा यार।
वही है ना, ये वाला फॉर्मूला कैसे आ रहा है, फर्स्ट फर्स्ट केस से आ रहा है ना।
ओ हाँ हाँ, ठीक ठीक ठीक, राइट।
हाँ, तो ये केस से फर्स्ट वाला फॉर्मूला आ गया।
नहीं ऐसे तो ये तो पैरेलल कॉम्बिनेशन का हुआ ना, वही तो इससे थोड़ा कंफ्यूज हो गए थे हम लोग।
ओके ओके ओके,
हाँ
then this can
ठीक।
be solved as again 1 by, so this will be k3 k1 comma 2 into k3 divided by k1 comma 2 plus k3। ठीक है, तो ये k इक्वेलेंट ही आ जाएगा ऑफ दिस सिस्टम, k इक्वेलेंट विल बी दिस वन। अब k12 जो है k1 प्लस k2 है, ऐसे आप पुट कर सकते हैं। तो देयर कैन बी वेरियस प्रॉब्लम्स। नाउ वन मोर क्वेश्चन एज अ होमवर्क आई विल गिव यू। You try this question when you have two masses m1 and m2. Now this is a not a single oscillator, this is a coupled oscillator. Okay, this can have different modes of oscillations. So you can try the frequency। ठीक है, इसका एंगुलर फ्रीक्वेंसी कैसे निकलेगा, you can try reading about it and we can discuss in the next class। Or you can think, you can imagine how does this system undergo oscillations, कैसे oscillate हो सकता है when there are no dissipative forces। Okay, so you consider it as a isolated system, ऐसा समझ लीजिए कि हवा में है और उस पर कोई भी, there is no other force, like it is not falling and things like that। Okay, and how it oscillates, you have to think about it। अच्छा, by the way, everything that we are doing here in IIT JAM for the preparation of IIT JAM examination is more oriented towards the problems, right? It has to be more oriented towards the problems. We as teachers understand it, that is why we give some problems in the class itself. But later on, if you want to go ahead in physics, ठीक है, फिजिक्स में अगर बहुत आगे बढ़ना चाहते हो, तो the focus should not be just over the problems, the focus should be ओवर थिंकिंग। ठीक है, थिंकिंग के ऊपर ही सब कुछ है, एवरीथिंग इज रिलेटेड टू थिंकिंग ओनली। लाइक फॉर एग्जाम्पल, when you go in MSc and let us say you want to get ahead and do a PhD, so your PhD interview is all about how you think, how you proceed when a problem arises. Okay, how you think. So it doesn't matter if you give the right answer, it doesn't matter if you give the wrong answer. It all matters how you think, how you approach the problem. Okay. So physics is all about thinking skills. Okay. It's not about just the imagination, it's not about just problem solving, it's not about just mathematics. So I think you guys know that Einstein had a poor mathematics. Okay. Still, we call him a very great physicist, right? Now, poor mathematics का मतलब ये नहीं है कि he doesn't know how to integrate x square. It is not that, of course. But he didn't have a conventionally very good mathematics. This is what I'm saying. Okay. But still, he got along because of thinking skills. Okay. Because of the thought experiments that he did and try to see the nature of reality as it is. Okay. Mm, Now I'll extend a little bit uh, to complete the things. Just give
Excuse
me a
me,
minute.
sir.
Yes.
The homework problem which you have given, so this
Mhm.
problem is actually means how to proceed this problem. Like, for example, in order to get the frequency, we have to have a displacement
Mhm.
either from the M1 direction or from the M2 direction. Or we can have from the we can stretch it from both the masses and we can leave it so that it can be oscillate.
Yes,
So,
yes,
sir,
yes. This is what you have to think. This is what you have to think, that
so
how
any
will the system oscillate?
But sir, as in these problems, like in some other problems, when they're attached with something or they are in a fixed position with something. But in this case, there could be multiple approaches in which we can solve and still get the same answer.
Yes, yes. So we can discuss this over WhatsApp or in the next class. Okay. So I'll finish off
Right,
what
sir.
I have to discuss.
Right, sir.
And
Right,
you
sir.
just try to think about this problem as how it oscillates, basically. So you can have different cases, of course, when this both are moved, okay, differently, x1, x2. Both are moved like this, x1, x2. Okay. So these are the two cases when the system will oscillate. And so you try how the oscillations will be there. So now let us discuss simple harmonic motion in gravitation. Then we'll also discuss a case where there are simple harmonic motion in fluid dynamics. Okay. A liquid column can also oscillate in an SHM. Okay. So this thing. So you see the force of gravity is proportional to 1 by distance square, right?
Right, sir.
Yes. This is the expression of force. Now, can you have something such that it oscillates into an SHM? So the answer is actually yes. Let us say this is a planet, or let us say this is Earth, and you have a tunnel which is dig through a cord, on this sphere. Okay. Although the Earth is not exactly a sphere, it is an oblate spheroid. But if you are successful in making a tunnel like this and you keep a mass inside it, okay, so what is the motion of this mass? Let us try to calculate it through equation of motion. Okay, so I won't spend a lot of time into the equation of motion. The conclusion is more important. So let us say there is a general position where this mass small m is, and this general position is r distance away from the center of Earth. Okay. Now at this general position, what is the force on the small m? Can you tell me what is the force on small m and where is it directed?
The force is directed towards the center,
Good.
and the force will be the small force will be dF is equals to G m dm by r square
Okay.
x minus r square.
X minus r. No, there will be 1 by r square, right? In the force.
No, you have taken a small distance, right? Small x
Acha,
distance
so you are saying small
with
r,
respect to a small. Yes, sir. Yes, sir. Yes,
capital
sir.
R minus small r. This is what you are saying.
Yes, sir. Yes, sir. Yes, sir.
So when the mass is inside when the small m mass is inside the sphere, what you can imagine is there is a smaller sphere. This is the smaller sphere. Like this. And through the smaller sphere, what you can imagine is there is a small sphere. This is the small sphere, not the big sphere. And a small m mass is kept. Okay, like this. At r distance, right? I'll draw it a little bit small. And outside there was a big sphere, but we are not right now imagining that big sphere. Let us forget that big sphere. Big sphere which is having capital R radius. So here the force of attraction on the small m mass on small m will be minus G capital M dash small divided by r, small m divided by r square, where m dash is the mass of this small sphere. Okay, if the mass of Earth is capital M, then let us say the mass of this small sphere is m dash. All right. Now just we have to calculate m dash in order to calculate what is force on small m. So again, we use the same concept of uniformity for calculating a smaller mass or a mass element, for example. Okay. So I'd explained earlier in the class that in physics, many times you use this particular approximation that you have uniformity in some things like, let us say, mass over here. So if there is uniformity in the mass,
dm
then the
by dr.
density. Yes, correct. So then you have same density at each point on the sphere. So if mass density is uniform, or the mass is uniformly distributed, you can say, then m dash by volume of the small sphere, that is 4 by 3 pi r cube, will be equal to, you can also write dm by dv, what you were saying, will be equal to total mass divided by total volume, 4 by 3 pi capital R cube. You can also use the elemental mass concept, but this is a simpler approach. So 4 by 3 pi gets cancelled. So m dash becomes this thing, m r cube by capital R cube. Okay. Now this is the mass, m dash mass of the small sphere. Now you put it into the force formula and get the force. Using the force, you can calculate the equation of motion. That is why we are trying to calculate the force on the small m, which will give us an idea of how the motion will happen inside a tunnel. Okay. So finally, force becomes what? Force on small m. We are doing this to write the equation of motion. Minus g, minus because it is directed towards the center. Outward direction is positive direction, radial direction जिसको बोलते हैं. Inward direction is negative, that is why conventionally we are taking a negative sign. G, capital M, sorry,
Small m r square by capital R cube.
small r cube by capital R cube. This is m dash, the small m
Hmm.
divided by r square, right? So r
Yes,
square
sir.
gets cancelled with the r cube, and you get minus gm by r cube, small m into small r, right? This is the force on m. So what do I see? I see that the force is proportional to minus of r, where r is the distance from the center, right? So at any point, this equation will hold true, right? It will hold true at every point inside the tunnel because we took a general point, right? This was the reason why we took a general point. So this is an SHM. This is the condition for SHM. Condition for SHM,
Right, sir.
which tells you that inside a tunnel there can be simple harmonic motion of a particle. Okay. Now you have to tell me whether this will really happen. अगर ऐसा हो जाएगा तो क्या सही में ऐसा होगा? क्या सही में पार्टिकल SHM करने लगेगा?
So
So
mathematically it can happen, but physically it cannot be possible as the digging up the tunnel is not so possible in that case.
So we have done experiments in physics where we have dig a cord. Of course, that cord was no way like this, but it was somewhat like this. This is how we, the scientists, have dig the cord. Okay? And this was done, by the way, for a particle physics experiment. This type of cord digging was done for a particle physics experiment. You can read about it. Actually, neutrinos were sent from one end of the cord, and a neutrino detector was kept at the other end. And why scientists did this was that to basically have a look at the neutrinos which have no effect on the other neutrinos which come from the outer space. Okay?
So you are talking about a neutrino hypothesis.
No, I'm not talking about the neutrino hypothesis, although theoretically you can use neutrino hypothesis by the experimental results of this particular experiment. But this was an experiment designed to see the properties of the neutrino, you can say, when there
Okay,
is no interference from the surrounding neutrinos which come towards the Earth. Okay? So there are
right.
trillions of neutrinos which pass through the surface of Earth. So to take out those neutrinos, this type of experiment was done. Anyways, you can read more about it. It is very interesting. तो
Okay, sir.
देन दिस इज द के. ठीक है. के निकल गया तो फिर टाइम पीरियड निकल जाएगा. टाइम पीरियड इज 2 पाई अंडर रूट m by k, right? So m divided by k, g, this thing. Okay. So it becomes 2 pi under root r cube by gm. So it is not depending on the mass of small sphere. It is not depending on the mass of small m. These two conclusions are there. Doesn't depend, of course, on m dash and small m. Small m पे depend नहीं कर रहा ये, this you should know. Okay. Now you can express it into a better looking form, that is, you know that gm by r square is nothing but g at the surface. Okay. At the surface of Earth, the value of gravitational acceleration is capital G capital M divided by r square, where capital M is mass of Earth and capital R is radius of Earth. So that is why T can be written as 2 pi under root uh, R by G, right? R by G. So comparing with the SHM, sorry, pendulum, simple pendulum. Simple pendulum was 2 pi under root L by G. Okay? Sorry, G by L. Sorry, L by G. So you can compare it with the time period of simple pendulum. Okay. To remember the value. And by the way, this value comes out to be 84.6 minutes. Let me check once again if this is 84.6 or 86.4. So you can do the calculation. 84.6, correct. So the time period of such a particle will be 84.6. So what I was saying was that experiments have been there where you have a cord passing through the earth, right? So is it possible that mass will oscillate in an SHM? The answer is actually no, because there will be dissipative forces which will be larger as compared to the net gravitational force. Okay, and the dissipative forces generally are proportional to the motion. So motion is nothing
Yes,
but
sir.
momentum, right? Or you can say velocity. If the mass is not changing, it the dissipative force is proportional to velocity, right? So that is why this practically is not possible, but ideally it is possible. Ideally, it has to be possible through the as dictated by the equations. Okay. Now there was a question asked in the TIFR exam related to this one. Okay. So I'll write that question down in this particular PDF for your reference. And also, if I dig a tunnel like this, so tunnel can have any shape, by the way. Even if I dig like this, or I dig through the center, for all such cases, the time period will be same, which is 2 pi under root R by G. Okay. No change in any of the cases. Now you can try deriving through the equation of motion when you have tunnel dig through the diameter. Okay. Now the question can ask you about some things like we have already derived about the time period, right? So one complete oscillation will take 84.6 minutes, right? But you could be asked different type of questions. So I'll guide you through a homework question and you try it and we can discuss it in the next class. No worries. Let us say you have a case.
Sir, excuse me, sir.
Huh.
Sir, may I quit? Sir, actually, I have to do my assignments for the college as well. So I
Sure.
can.
You can go. You can go.
Sorry, sir. Just because.
No,
Uh,
I was about to finish only. No issues.
okay. Good night, sir. Thank you.
Good night. Bye.
Bye.
Now you could be asked a question where mass m is over here, and it is being given a push. Okay, it is being given a push. So there is some initial velocity v naught over here, and that velocity is not zero. So you have to find, by the time it reaches end of the tunnel, the final point, this is initial point, what is the time taken? So time initial to final is what? And it will not be equal to t by 2. Okay. So you have to try this type of question, and then we'll meet in the next class.